This is an example of the kind of calculation you'd have to do if you wanted to calculate the pH of a weak base in water. The question, calculate the pH of 0.010 molar codeine. And it says that codeine is a base. I've listed here the steps for determining the pH of various weak acids or weak bases in water. I'll not go through them now, but let's look at them one by one as we go through the problem. The first thing we have to ask ourselves is the given compound acidic or basic in water? Well, that's easy, because I told you here that it was a base, but many times you will not have that information, and you will have to know which compounds are acidic or basic. Codeine is a nitrogen-containing base, very much like ammonia, in that the nitrogen is the cause of the basicity. Sometimes there are carbons, hydrogens, even oxygens, as in codeine, and you will have to recognize that kind of structure. Well, that's decided, so now we need to write our net ionic reaction equation. And we're going to produce OH minus because the compound is a base. See down here, base compound has to have the OH minus produced. Let's write that net ionic equation. C18, H21, O3, N. The reaction is going to go plus water. You're always putting water on the left side here. And then you're going to produce the compound on the right, which is the conjugate acid of the base, if you have a base. So that's C18, H21, O3. And what's different about a conjugate acid compared to the base? It has an extra H+. In the case of these nitrogen bases, the H gets attached to the nitrogen, the lone pair of the nitrogen, and you would write the plus next to the structure. I like to put the H right next to the nitrogen, which is really where it is. So there we have our net ionic equation showing that we're producing OH minus from the base. Next, we will usually be looking up a Ka or Kb value to go with the equation we just wrote, and then set up an ice table. Well, here we've been given the Kb, so that saves us one little step, but let's write up the ice table. We're given that we have 0.010 molar codeine, so that's going to be your initial molarity, and when you're not told anything else, then those other compounds are zeros. As usual, our water, which is a pure liquid, will be left out of the ice table. To go to equilibrium, we're going to have to fill in the zero spot, the usual thing, plus X, you get X, minus X for the reactant here. Again, all 1-to-1 molar ratios when you have our acid-base reactions. Our next step will be to put our equilibrium values from the ice table into the equilibrium constant expression and solve for what is needed. So we're going to set up Kb equals, it will be x squared, x times x, over the 0.010 minus x. So here's our equilibrium constant expression to solve. To simplify the math, we're going to do our usual trick of assuming that x is small compared to the number it's subtracted from. So here we will assume that x, or actually 0.010 minus x, is approximately equal to 0.010. That makes the math much easier. So you have 8.9 times 10 to the minus 7th equals x squared over 0.010. That means that x squared equals 8.9 times 10 to the minus 9th, and x equals 9.4 times 10 to the minus fifth. You will notice now that that number, 9.4 times 10 to the minus fifth, is small compared to 0.010. You wouldn't even see it if you subtracted those two and rounded off to the proper sig figs. So our assumption that we wrote here, it's okay. So we have our x equals 9.4 times 10 to the minus 5. But what is x? Is x H3O plus? No, remember we had a base here, and in our reaction equation we produced OH minus. So the ice table had OH minus as a product, and x is actually the concentration of OH minus. We need to change OH minus into pH. That would be a two-step process. One way to do it is, instead of going from the OH minus to the H3O plus directly, we could do the POH, and that is defined like pH. We would do the POH as the negative log of 9.4 times 10 to the minus 5. That comes out to be 4.03. Note that in my logarithmic number, my answer to the log problem, I have 2 decimal places, because up in my original number, I had 2 sig figs. 2 sig figs goes to 2 decimal places. Well, that's POH, and the relationship between pH and POH is POH plus pH equals 14, which comes from the kW, which is 1 times 10 to the minus 14th. So you're going to take your 14 minus 4.03 to equal 9.97. And that should be the pH. You can use this method also to solve for something other than pH. In fact, you may even be given the pH value and asked to calculate something else, such as Ka or Kb. If you're given the pH value, you can use it to calculate either the H3O plus or the OH minus at equilibrium, and then put that number in your ice table.